Flipping a switch is easy, but in museums and retail spaces, every single photon impacts color accuracy and art preservation. To master this, we will analyze advanced LED spectrum technology and apply it through modular magnetic beam steering hardware. We will specifically learn to render crisp whites, make warm colors vibrate, and safely steer light to protect sensitive pieces from degradation. Advanced lighting design relies on managing these physical variables to ensure objects appear vibrant while remaining physically protected from decay. Historically, natural daylight has been our standard for perfect color rendition. But daylight carries a critical flaw for indoor environments. It contains highly damaging ultraviolet radiation. To avoid UV, lighting designers frequently use standard blue-based commercial LEDs. However, these fail noticeably when illuminating white fabrics and paper products in retail displays, leaving surfaces looking flat and slightly yellowed. The reason comes down to fluorescent whitening agents, or FWAs. These are chemical brighteners embedded in modern clothing, plastics, and paper to make them appear artificially whiter. This chart shows the emission spectrum of a standard LED. Notice how the blue LED wavelengths completely miss the FWA activation zone on the far left. FWAs remain dormant under these lights because they require short wavelength violet light to become excited and re-emit visible white. Advanced full-spectrum LEDs are engineered to solve this. They extend their emission curve specifically to provide that exact violet wavelength, activating the FWAs without crossing the threshold into harmful UV radiation. True white rendering requires a precise chemical interaction driven by the perfect spectrum, rather than a simple increase in brightness. When protecting artwork, eliminating UV is only the first precaution. The primary cause of physical degradation is the total volume of light hitting the object, a metric measured as illuminance. Reducing a room's illuminance from 300 lux down to 30 lux increases an artwork's lifespan by a staggering 1,000%. There is a secondary, frequently ignored threat in gallery settings: poor beam distribution and optical spill. Look at this graph comparing a precision 10-degree lamp against a standard 15-degree competitor lamp. The competitor dumps 20% of its energy entirely outside the intended target area. That excess light in the shaded blue region creates accidental damage. Safe lighting requires engineering the minimum necessary lux combined with absolute mathematical beam precision. To achieve that precision on the fly, we use the self-centering magnetic snap system to physically manipulate the beam and spectrum post-emission. The physical experience relies on a precise magnetic force, ranging from 0.45 to 1.0 pound force. This ensures the accessory automatically centers itself on the lamp face, requiring zero tools. For color modification, the Enhance filter alters the spectrum to specifically boost the vividness of warm colors, like reds, oranges, pinks, and greens. Beyond color modification, structural beam steering requires a different approach, introducing the AimSnap accessory. The AimSnap relies on two opposing lenses. Rotating them against each other bends the light beam up to 20 degrees off-center. Aligning the tracking marks narrowly creates maximum deflection, while widening the angle reduces the bend. True dynamic lighting requires the physical capability to dictate the light's exact behavior long after it leaves the diode. Modular systems have a specific vulnerability. Placing these accessories in the wrong order actively degrades the optical effect and ruins the beam shape. The immutable rule of stacking is straightforward. The filter that modifies the color must always be closest to the physical lamp. For a maximum configuration, follow this exact three-step sequence. First, apply the Enhance snap. Second, add the CCT Shift snap. Finally, place the beam shaping snap on the outside. When combining multiple lenses with linear textures, you must rotate one slightly off-axis to prevent undesirable optical artifacts and distortion. Adhering to this exact stacking protocol transforms a loose pile of filters into a unified, high-performance optical engine. We've deployed violet light for FWAs, enhanced our warm colors, stacked filters sequentially, and steered the final beam to the target. This setup produces theatrical levels of contrast and vibrant color rendering, all while adhering to the strict low-lux safety limits required for preservation. You now possess the architectural and biological knowledge required to engineer these professional lighting outcomes from scratch. Mastering light isn't a search for the brightest source. It's a careful trade-off between vivid color rendering and the physical survival of the subject.